Hello everybody, and welcome to example 3 on page 34 of the workbook. This is another example of finding the volume of a solid of revolution. Let's read this problem together. Okay, so they would like us to set up but not evaluate an integral that gives the volume of the solid region generated by rotating the region bounded by y equals x and y equals x squared about the line x equals 2. Okay, so notice the instructions here. Set up but do not evaluate. So all they want from us is an integral in this case. They'd like us to figure out what function do we need to integrate to find the volume, and then to figure out the limits of integration, and then to stop. We don't actually need to do the integral in this problem. Okay, so as we've been doing, we'll try to start with a picture here, just a rough sketch. So y equals x and y equals x squared. We've got a line and a parabola, and very roughly speaking, the parabola looks like this, and the line looks like this. So you can kind of see the region in between that they're talking about right there. Okay, and I'm going to, just because space is tight here, I'm going to erase that sketch and just try to draw a more zoomed in picture of that. Okay, so let's get rid of that. Just redraw the part that's in between those two curves. Okay, and it looked like I'll leave a little space over on the right for us. Okay, it kind of looked like that, the region in between that line and that parabola. Okay, we kind of know from previous examples that we've done that the points of intersection are probably going to be of interest to us, so why don't we get that part out of the way over here. That'll help us find our limits of integration, hopefully. Okay, so points of intersection, we'll just take those two curves and set them equal to each other. So if x equals x squared, then get everything on one side, and that turns into x squared minus x equals 0. We can do a little factoring. Okay, and it looks like we're going to get crossing points of x equals 0 or x equals 1. All right, we'll kind of file that away and use that fact when the time is right here. Now let's see how they're actually describing the solid to us. So they'd like us to take this region and to rotate it about the line x equals 2. That's a little bit different of an axis of rotation as what we've seen before. We know from our work that we did before that x equals 1 is sitting over here. That was one of our points of intersection. So our axis of rotation is actually over to the right here. Okay, and I'm going to, just so that our picture doesn't get too big, this is not going to be quite to scale. X equals 2 is probably a little farther to the right than I'm drawing it, but I'm going to draw it there anyway. Okay, and what you want to imagine is taking this region over here to the left, okay, rotating that whole region through the line x equals 2. So think of x equals 2 as being a big mirror, and every point is going to kind of go straight through that mirror and come out an equal distance on the other side. Okay, so this point's going to wind up here. This point is going to wind up way over here. Okay, and the mirror image is going to kind of look like, I'll draw it dotted. Okay, kind of like that. All right. And now it is machete time. We're going to take out our machete and slice this. And the thing that I will keep reminding you of is you always want to slice perpendicular to your axis of rotation. Now in this case, that means that we are going to be slicing in this direction, left to right. Okay, notice that there's a big gap in the center of this region. Okay, and so for your slice, you are going to get a big washer that kind of looks like this. There's our typical slice. Okay, and as we've seen before, the key to coming up with a volume integral here is measuring the area of that slice that we just took. Okay, now here comes a really important question for you. Okay, as you look at the radii of this washer that we've just drawn, okay, I'm going to draw the shorter radius. Is that radius a horizontal or a vertical distance? Is it a horizontal or a vertical distance? I'm going to draw it. You can see from the picture that it's horizontal, and that's important because it tells us what variable we want to solve for. If we want to measure that horizontal distance that I just drew in, what's going to be of interest to us is the x value here and the x value here. Okay, we need to figure out those two things. Okay, I'm going to go ahead and also just draw a top view of this slice so we can kind of fill in our radii as we figure out what they are. Okay, so what about that problem of figuring out what the x values are at these 2 points? Okay, well, you can probably see from the picture that here, right on the axis of rotation, x is equal to 2. We can see that down here from the picture that we already drew. But what is x going to be equal to over here? Well, there we have to ask ourselves, what curve is it that we're looking at right here? Okay, that curve was y equals x squared. And so what would you get if you took that curve and solved it for x? Okay, you would take the square root of both sides, and you would get x equals the square root of y. And that tells us, okay, what x is equal to at that point. All right, so how would we measure this horizontal distance then? Well, the idea would be we would just subtract these two x coordinates. So we're going to take 2, because it's on the right, and subtract the square root of y, and that's going to measure this horizontal distance. So I'm going to go down to the picture here, and I'm going to fill in that inner radius with 2 minus the square root of y. That's how long that has to be. Okay, the next thing we need is the bigger radius, the outer one. Okay, and going back to our picture, that's going to be the distance from here to the center. Okay, meaning that we need to know what the x value is at that point. Okay, so we ask ourselves the same question, what curve are we talking about there? Well, that's the line y equals x, and that's the same formula as we just turn it around and say x equals y. Okay, so x is equal to y at this point. And then we ask, how do we measure this entire horizontal distance? Well, we're just going to subtract the x-coordinate at the right from the x-coordinate at the left. So we're going to take 2 minus y. That's going to give us that horizontal distance. Okay, and we are ready then to write down a volume integral. Okay, so we're going to get the integral of the area, and remember we're talking about the area of this washer here, so we're going to take pi times the outer radius squared, that's the area of the bigger circle, minus pi times the inner radius squared. Okay, and this is getting a little cluttered, so let me just separate that a little bit. Okay, and what's missing are the limits of integration again. Question for you. Are the limits of integration going to be x values or y values in this case? Okay, well, if you look at what's at the end of our integral dy, that answers the question for us. They need to be y values because we've got y's in our integral. Okay, so unfortunately, our algebra gave us x values, not y values, but we can figure out what the y values are. Okay, because both of those x values happen to lie on the curve, or the line, y equals x. And so if x is 0 and x is 1, that means that y is 0 and y is 1, because y equals x at those 2 points. Oh, whoops, sorry. I wrote y equals 0 twice. Okay, so our limits turn out to just be 0 to 1 in this case, and remind ourselves that they wanted us to just set up but not evaluate the integral, and so we're actually done with this problem at this point. Okay, this is the integral that would give us the correct volume if we were to evaluate it.